Thank you. Thanks for waiting.
Let me start to share my screen. Just let me know once it is up.
Yeah, I'm just looking at Purnima, have you started recording? Oh, thank you. I've started.
Yeah.
Thank you.
Sure.
Please.
Thanks, Professor Aprajita. Thanks for such a nice introduction. And I do recall our my visit to IIIT Jabalpur for deep learning workshop, and great to be here again. So, like Professor Prajita introduced me, I'm Rishu Gupta from the application engineering team at Mathworks. The focus for today's agenda will be how we can leverage artificial intelligence, machine learning, and deep learning into medical imaging workflows. Let me get started with the high-level agenda that I have charted out for today's discussion. I'll be going very brief as to what is image processing, what is computer vision. It will be very brief. It will be very brief, followed by I'll be talking multiple applications around medical imaging. I'll be talking about how you can do the automated detection and quantification of infections in a blood smear images. Therein, I'll be talking about a lot of the different workflows and methodologies when it comes to image processing, like image thresholding or connected component analysis or region analysis, or I'll be also touching upon morphological operations and how can these be helpful in doing detection and quantification and avoiding the need of going into machine learning and deep learning. Then I'll be also going into a little bit more details. I'll be talking about different kind of parasitic infections that may happen in blood smear images, and I'll be using machine learning as a technique to classify those parasitic infections looking at the image. We'll try to build a machine learning model, and we'll also see aspects of how, if at all, I wanted to take my model and I want to deploy my model into different platforms, how can that be done? So I'll be talking a little bit on the deployment as well, how you can compile your application into our algorithms into a form of an app which can be deployed to other platforms. Then the last application that I'll be going into would be semantic segmentation of left ventricle from the cardiac images, where I'll be talking about using the MRI images and using deep learning as a technology to establish the workflow of segmentation of left ventricle. Now, when we are talking about all of these different applications, I can clearly see the first two applications when we are talking about parasitic infections or classification of parasitic infections. They're mostly working on the images, or we will be working on the 2D pixels. However, the third application which I'm talking about, we will be working on the voxels or multiple images stacked together from the MRI that we are capturing from tissue or a body. In this case, left ventricle. Some of the important aspects when we talk about these medical images is how to handle large images, because when we are talking about histopathological images in general or microscopic images, the size of those images can go significantly large. It could be 1 GB, 2 GB, 3 GB, similar to satellite images. They can be very large in size, and hence it is very difficult to process those entire in the hardware. And we need some ways to analyze and process these large images. So I'll be also touching upon how you can work on those very large images while working on MATLAB. And throughout the presentation, I'll be showing you a lot of videos wherein I'll be establishing the entire workflow in MATLAB. Great. Now, post setting that context, let's get started with what is high-level image processing and computer vision. A very quick introduction to image processing and computer vision could be these two domains go very much hand in hand. Image processing is often and generally done prior to computer vision to learn something about an image. Image processing is more about manipulation of image to extract meaningful information, as in this case could be counting the number of pixels in an image. Right. However, in the case of computer vision, it is more about understanding an image or teaching computers to understand scene. For example, this is a letter L. So image processing is mostly around working with the pixels on the image, and computer vision is more around understanding the images and getting the information out of it. That was very high level introduction to what image processing and computer vision could be. Now going ahead, an image is a matrix of intensity values. The intensity values can vary from 0 to 255 depending upon I'm working on the 8-bit image or a higher bits images. And when we are talking about color images, then it could be RGB channels stacked together with each individual channel having a pixel value from 0 to 255 bit. Now, if I look at this particular example here, what we are trying to achieve here, or the goal for this particular application for us would be, on the left, what we are seeing is the blood smear images. You are seeing RBCs on the image. And on the right, you have done some analysis on this image, which could be a simple image analysis, or it could be more advanced deep learning, machine learning. So what we are seeing on the right image is we are trying to quantify the number of blood cells. We are also trying to quantify and detect the presence of the infections in these blood smear images. And on the right, what you are seeing is the babesiosis infection, and we will see a lot more about it. Now, when we try to work on these applications, the workflow, when we refer to the conventional image processing way, may very well go with the probably starting with the thresholding and then doing some connected component analysis to filter out the mask that we have created with the thresholding, followed by some more advanced segmentation and quantification methods to identify either the circles or to identify where the infection is in the image. So let's go ahead and see how these things can be established inside MATLAB right away. So the first thing that I wanted to introduce you with is something called as a color image thresholding. What is thresholding? Thresholding is putting a upper limit or a lower limit onto the number of pixels which should be accommodated inside an image, and above or below those should be nullified. This helps us to analyze the image of a particular contrast and also to get more information on the images where there is a significant contrast available. Now, these applications or these approaches may work very well for some of the simplistic problems. Probably here what we are talking about is babesiosis infection detection. This could be a little bit of a simplistic problem, so probably conventional image processing algorithms may work. However, when we start to look at more advanced problem statements, then we will see how conventional image processing may not be the right approach, and we may need to merge into some advanced techniques like machine learning and deep learning. So with that, let me just go ahead and open up the color thresholder app and see how and show you how color thresholder app can help us to do the segmentation. Now, the three different kind of parasitic infections that we are going to talk about is, the first is babesiosis, second is Plasmodium gametocide, and the third is trypanosomiasis. So these are the three different kind of parasitic infections that could be of many that could be available inside the blood smear images. Now, if I look at the images of babesiosis, then these could be the image. This is how the images may look like. Now, starting, the first thing I may want to do is, since while we are working on these large images or while we are working on medical images, generally the data set could be very large or the size of the images could be very large. So we may, if at all we have the capabilities of multiple compute resources available, or if we have the capability of multiple GPUs available, we can directly invoke those things with the help of GCP command inside MATLAB. So with GCP, I can enable the parallel computing and scaling my computations from a single core CPU to a multi-core machine. In my machine, there are 4 cores. So what you see here is the MATLAB is now connected to take the advantage of all the 4 cores within my machine. Now, the second thing that I want to highlight here is that I'm going to use throughout my discussion today is image data store. Now, what is image data store is, while you are working on a large data set or large images, image data store comes in very handy, or data stores in general. Inside MATLAB, there is a concept of data store which allows you to work on very large set of data. And irrespective of where your data is stored, whether it is stored on a desktop computer or it is stored on a cloud services, you can directly start to process these data with the help of, or you can directly get the handle to this data with the help of image data store. Now, why this image data store becomes important is because if you're working on very large images and you do not have sufficiently large RAM, so while you try to bring in all those images inside a framework, it may shoot out of memory error. So image data store not gives you the entire data, rather it gives you the pointer to that kind of data. So you can use the data as and when required going ahead in the development process. So first thing is I'm using this image data store. I'm using this image data store to read in all the images that are available to me for my application inside the folder, which is blood smear images and babesiosis. So let me just get it started. Use image data store to read in these images. And once I have these images stored inside, information of these images stored inside data store, there are a lot of different functions and functionalities that are associated to this data store. For example, if you want to read a certain image inside a data store, if you want to read all of the image, if you want to just do a preview of some of the images, or if you want to combine the data store coming in from one source to another source, there are a lot of different functionalities that you can invoke. Also, later in the discussion, there will be a lot of things that we'll be talking about augmentations. So augmentations and all such things can be directly operated on the image data store. One such function that I wanted to highlight here is read image. So methods are basically functions inside MATLAB. So one such function that I want to invoke here or call out here is read image. I'll pass the image data store and I'll pass the number of the numerical value of the image that I wanted to analyze. So I'm passing here 4, 5, 6, and as I pass on, I can start to see the different images and I can visualize what my entire data set looks like. Here for the simplicity, I have just taken 16 images, but it could be thousands of images when it comes to building of a robust algorithm inside medical imaging. Now, once I have read in my data inside the MATLAB, or once I have some certain pointer to my data inside MATLAB, the next thing that I may want to do is I may want to start invoking some of these capabilities around image processing. We talked about some of these keywords like thresholding, connected component analysis, segmentation, counting the number of pixels, and all those things. So first thing is all of these things that we are going to talk about or we are talking can very well be established in MATLAB on the command line interface. You can do the scripting. Also, MATLAB helps you do all these things at the higher level as well. So you can interactively work on these apps to build your application and then use these algorithms in the programmatic API to scale it to all the data that you have. So there are a lot of apps available inside image processing and computer vision section here. Let's get started and start to use one of the apps which says color thresholder. Now, once I invoke color thresholder app, the first thing that I will need to do is I need to load the image. Either I can load the image from my workspace or I can load the image from my folder. Now, one thing that this color thresholder app shows you out of the box is different color spaces in which you can visualize your image. Now, this also becomes very important because many a times RGB color space may not be the best color space to classify or to do the segmentation. So at the start itself, you can visualize a lot of different color spaces. You can start to see what color space gives you good bifurcation on the color for your image. So here I have RGB, HSV, YCBCR, and LAB. And I have chosen RGB, but like you can choose any different color space that may seem more relevant to your application. Once I have RGB color space, I can quickly start to modify these sliders and do the real-time visualization of how these different thresholding components or thresholding values may operate on my algorithm. There are a lot of different ways to do that. You can either start to do simple masking of these pixels in order to get the right value of the threshold. You can look at the scatter plot to get the right threshold values. And I'll also explain why these thresholding becomes important and why this visualization becomes important. So here I have just done a simple thresholding. I'm overlaying the image back onto it and seeing how much of the thresholding is appropriate or not. And I can also export the binary mask or the image that we are working on. I can also export the function out of the box from this app or any of the app that I'm working on. And here, if you see, this is the mask that I have created. And this mask has all the information like what kind of color space I was working on, what are the different channel thresholds that I have decided. Now, one of the advantages to get this as a function could be, I have this identified for one of my images, but now I want to use this to apply to all of the different data set of images that I have. So all these things become very important. And while you are doing the visualization and analysis at the same time, you can very effectively do a lot of different comparisons, a lot of different modifications in order to save a lot of time that you can then apply to more complex workflows. Now, perfect. Now, this is the outcome that we just talked about of the color thresholding. Now, once the color thresholding is done and we have certain outcome from the color thresholding, I can start to look at what are the flaws in these output just by doing simple thresholding. I can see a lot of different artifacts getting introduced, a lot of different artifacts available. There are a lot of different blobs that are available inside the regions that we have segmented. We may not want to have all of these things when we are doing some analysis, or we may want to do some analysis or counting of the pixels. So to do that, one of the things in the image processing that you may want to do could be connected component analysis, or you may want to apply morphological operations. Now for connected component analysis, also inside MATLAB, there is again a set of apps that is available. Now again, to invoke these apps, you can go to image region analyzer from the image processing computer vision section. You can invoke that. And what image region analyzer will do, and what connected component analysis actually does, is gives you different properties on which you can actually compare the image or the mask that you have created. And those different properties could be area, major axis length, eccentricity, and many more. Once you start to do the analysis of these algorithms on that, yeah, sorry about that. So once you start to do that analysis, you will realize like what particular property could be a best fit for your use case. Now here I feel like I can use the area as a property to remove some of these smaller blobs in my image. And what I'll do is I'll just quickly pick up the number of the pixels that I may not want, or number of pixels wherein the blob size is greater than 100 pixels. I just want to quickly remove that. And if you see, once I did that, I do not have any more blobs, and my black region in the mask is very clearly sorted out. So connected component analysis helps me to achieve all of these things while looking at the connected component analysis from multiple different properties perspectives. Now, the other thing that I may want to do is, if I see these blobs which are important for me, I can see small holes within these blobs. And this becomes irrelevant if we are trying to count the number of the pixels within these RBCs. So what I can do is I can simply choose these fill holes, kind of ready to use functionalities, and fill these holes, which will give me a smooth blob or a smooth area around the RBCs that I'm looking at. Now, similar to the color thresholder app from within the image region analyzer, also I can export these functions and functionalities and club the functions that I have created using the color thresholder app and club the functions that I have created using image region analyzer, and build an entire algorithm which will not only do thresholding as well as the connected component analysis in the batch processing mode. Right. So I can export this, and once I export this is again exported into a form of a MATLAB function, and you can see all these connected component analysis with the help of region props that we do, or some of these thresholding applications that we have done out of the box, or the whole filling operations that we have done from the app gets incorporated within the algorithm itself. And these can be established on any of these different properties that could be relevant for the application that I am working on. So first thing that I did was connected component analysis. The second thing that I did was region analysis, or first thing that I did was the color thresholding, and the second was the connected component analysis. And post the connected component analysis, what I got was some clear identification of the RBCs that I may want to look at. Now, this could be one of the ways in which I'm trying to identify where are my RBCs and what is the area of these RBCs. Right. Now, many a times we may be required to do the counting of the pixels, or also understand the number of RBCs within the image. And for that, some more advanced algorithms, let's say for segmentation, the algorithms like watershed algorithm becomes important. Or I may just wanted to look at the contours of the RBCs or the color contours of the babesiosis or the RBCs that we are looking at. Now, once I have those images inside MATLAB, I can quickly use some of the segmentation techniques like watershed and many others from within the command line or from the app itself. And once I have those, I can start to create the mask for my particular application. And once I have those masks ready, I can go on to find the circles within the, if we are considering RBCs as a circular region, then I can quickly go ahead and try to identify those circles from the blood smear images. Now here again, this is another app, which is image segmenter app, which will allow me to import the image that I may want to work on. I can also import the mask that I have created, right? And if you see on the mask, I already have clearly delineated some of these RBCs, and many of these RBCs that we see are circular in nature, right? Now, one of the things that I can do is I can use the capability within MATLAB to identify the circles. And to do that, there is an implementation. However, you will need to parameterize, choose the correct appropriate parameterization of your algorithm with all the sensitivity and whatever is required. And once you choose all these different components or parameters, you will see that immediately the algorithm would be able to identify the circles, which if we are calling as RBCs directly into in the image. Now, once we have this identify, I can also try to understand different kind of analysis that a pathologist or a radiologist may want to do, like what is the size of the RBCs within an image, or what are the number of RBCs within the image, and so on. I can again, like whatever the application we are doing here in the image segmentation or image segmenter, I can again export these out, all of these things, and I can use all of this information to get to or the plot the circles over my RBCs. And here, like there are in total 17 RBCs that I have identified from the one image that I was working on, right? But while I'm working on these kind of data, I may not be dealing with one image only. I may very certainly be dealing with thousands of images. Now, when we are dealing with thousands of images, it becomes important for us to be able to scale our application and use that application with all the different images that I have worked on. Now here, what I have done is I have actually taken all these three different algorithms that we have implemented, the algorithms to find the circles, the algorithms to do the simple thresholding, as well as algorithm to do connected component analysis. And to bring all of this together, I have created a function named as refined mask. And I will invoke something called as a batch processor. Within batch processor, I will bring in all of these different images that I wanted to process. It could be thousands of images, it could be millions of images that you may want to process. And now the next thing that this image batch processor will allow me to do is use all the compute resources that I have available on my system. I can process only the selected images with the algorithm that we have implemented, or I can go ahead and process all of the images in one shot. So I can choose to be exceptional on what kind of images I may be working on. And as you see, as you process the images that with the algorithm, which we have implemented inside refined mask 2, this actually gives output to me for all the different images that I may want to see. If you have observed here, like we have developed an algorithm for one image, but now we are trying to bring all of these pieces together and applying this to the entire data set. I can also export whatever we have done here in the form of the function, in the form of the images, in the form of the data store, and a lot of things. And once I have this information incorporated or extracted, I can choose to share it across with different radiologists, pathologists for analysis, for ground truthing, or many different tasks that we may be required to do in order to process these images or build the end application. Right. Now we talked about The workflow, when we are referring to image processing or computer vision based methods for doing the analysis of babesiosis parasite within a medical image, we introduced some of the apps that could be useful to do these kind of analysis. Like we introduced color thresholder, I talked about image segmenter, I talked about image region analyzer, I also touched upon the image batch processor. But these are not the only apps that are available inside MATLAB while you're working on image processing computer vision. There are a lot of different workflows available, a lot of different ways to accelerate your workflows that are available while you are doing your algorithm development. There are a lot of examples which are also available to get you quickly started. And the intent of these high level workflows is to quickly make you adapt or understand what the end use case for the application could be, and also to quickly generate code from there and continue to work progressively on your particular problem statements and quickly hit the bottleneck as to where the research is required, rather than not investing too much time on what has already been done or what has already been accomplished. Quickly establish what is there and then quickly move on to the next concept as to what could be the next thing that I could be working on. Right. So that was one of the use case wherein I was trying to do the detection of the red blood cells inside the blood smear images. The other application that I may want to work on could be very much around the identification of different kind of parasitic infections from the blood smear images. And these different kind of parasitic infections could be babesiosis, it could be Plasmodium gametocyte, or it could be trypanosomiasis. So there could be a lot of different kind of infections that are available. And it is very difficult for pathologists or radiologists to right away look at these images and give the inference of it. Or let's just say, even if it is easier for the radiologist and pathologist, there is a requirement for automated systems which can give these classifications out of the box to assist or provide a second opinion to the radiologist and doctors. So let's go ahead and try to see how we can build some application using machine learning this time, wherein I'm doing the classification of these parasitic infections from the blood smear images. Now the challenge here is all these images look very similar, and how we can identify what parasitic infection is present in the slide that I am looking at right now. There are a lot of different things that we may want to do while we are doing the manual analysis, like we may want to do the enhancement, we may want to do the resizing, or if we are even going for more of a complicated workflows like deep learning or machine learning, we may need to have a lot of augmentations around the data in order to get to that level. What we can do is we can use some of the computer vision or machine learning based workflows to get quickly started and see how we can establish the entire workflow. Here we are trying to identify the RBCs which are infected. So if you look at this particular image, we will see that there are 35.3% of the infections in the given region that we are looking at. Now this is one image which I'm doing the analysis, so it is easier to look at the image and probably do a very astute analysis of that image, but there could be thousands of images that I am working on, and I need some automation algorithm to help me on that. Right. And that could very well be established with the help of these computer vision and machine learning kind of workflows. You can build your own predictor, which will, once fed an image, will be able to tell you whether the image has babesiosis or any other kind of parasitic infection. What a typical machine learning workflow may look like for image category recognition or classification of the image into different classes. First thing is, our intent here is we have the image that we may want to work on or that we may want to classify. We take an image, and my algorithm, whatever I'm working on here, should be able to classify that image into many different classes. And those classes could be pertaining to what is the infection within those image. Now, there could be two approaches to this kind of problem statement. One is we go to radiologist, pathologist, and get some handwritten rules that if this is visible inside the image, that image becomes, or that image can be categorized to a babesiosis or any other classes. But that would again require you to pin down exactly the thing that we have done in the previous section. Probably get certain algorithms for individual section, probably one algorithm for brightness identification, one for edge density, one doing analysis on the different components of area, probably eccentricity and many other things. And then club all these things together and get an algorithm which can do the classification for us. In essence, what we are trying to do is we are trying to look for the features in the image that can help me to classify these images belonging to certain classes. Now, the other approach, other than the handwritten program, or let's say a sequential program doing analysis of individual components to identify the different classes, the other thing that we can do is we can probably try to establish more automated workflow, and which can come via machine learning or deep learning kind of workflows. Compared to the conventional workflow, what happens in the case of machine learning workflow is, in machine learning, you can extract a lot of features from the image. And those features could be very specific to the application that you are working on, or they could be more generic as to a lot of different features that are available inside, or more of the statistical features that you can analyze or extract from those images, which can be used in conjunction to a lot of different other features to build a machine learning model. In the case of machine learning model, what would be required is you would need to have a lot of data. So data is nothing but images that we are looking at. And you also need to have a label. And the reason for that is because when we are going for any learning based algorithm, the first thing that is required is, if it is a supervised learning algorithm, first thing that is required is we need to have a data and the labels associated or the outcomes associated to that data. For example, if we are looking at these three images, these three different classes, we should have a lot of different images categorized already into these three different classes, so that my predictor or my model can learn from these images and give me the classifications as appropriate. Right. So in the case of machine learning algorithms, what is required is the input would be a data and it would be a label, and what comes out would be a model. And model could be lot or many different kind of models that are available or that could be trained depending on your application for machine learning for the medical imaging. Now let's go a little bit more, look into details of these workflows. Now, the first thing that happens in the machine learning workflow is we have a lot of images, which is termed as a training data. From the training data, we extract features. There are two ways to approach this. One is either we extract a lot of features from the image by having no domain information. We can continue to extract a lot of statistical features. We can continue to extract a lot of more complex features, right? More the features we have, more fidelity we can have on the models that we are building. Or we can go to a radiologist and ask them, what are the features that you see differently when you are trying to identify certain pathology in the given image. Now, given the information we have, we can extract the features from the training data. Once we have those features, we will use those features to train a model. There could be a lot of different kind of models that we may be working on, and different kind of accuracies we may get on different kind of models. We could be working on linear regression, logistic regression. We could be working on support vector machines, ensemble classifiers, decision trees, and many kind of different machine learning models. And you would also be understanding that if there are a lot of different models, how do we choose what models is best for my application? And we will reach to that challenge as well. Now, once you have the training data, you have extracted the features, you may want to go ahead and train your model. And once the model is trained, you will have your classifier or a model available to you. Now, once you have the model available, you may feed in the image to the model. There will be a pre-processing pipeline, which will again extract the similar kind of features that you have extracted while training of the model. You will extract those similar kind of features from the test data as well. And once those features are extracted, if the model is correctly trained, it will give you the classification as correct. If it is a hat, it would be hat. If it is a babesiosis or the kind of application that we are working on, it could be those kind of outcomes. So two steps to it. First is the training, and another is the testing. In training also, the one thing that is common both in training and testing is we do the feature extraction, and the feature extraction step should be identical whether it is in the training step or in the testing step. So once the feature is extracted, we go ahead or train the model, and during testing, we take those features and feed it to the trained model and get the classification. Depending upon how robust and accurate my model is, I'll get the appropriate outcomes. Now let's try to establish this particular workflow of machine learning inside MATLAB. And right now I won't be talking about data labeling. I'll be talking about data labeling when I go into the deep learning section. Now in here, the application that I'm going to work on is the classifying the parasitic infections in blood smear images. There are different kind of infections that we are going to look at. The steps that we may want to do while we are trying to establish these workflows is the first is the pre-processing, whichever is required, and pre-processing may employ extracting a lot of different features or clearing out the data which is irrelevant and many other things. The modeling piece would be where I would choose what kind of models I want to train, or I would be training a lot of different models and seeing what models best work for my particular applications, and try to get to accuracy and robustness that I am looking for my application. The third piece would be taking your application and deploying your application onto certain platform, or taking your application and packaging your application into a format which can be then deployed or shared across with multiple users or multiple hospitals across the globe, or within organization as a training module. Now, again, let's go ahead and look at some of the images that we may want to work on. It's the similar images that we have used for the kind of analysis that we did using image processing computer vision. And if you have observed, the parasitic infections that we were looking at in babesiosis are very different from the parasitic infections that we are looking at in different other use case. Right. And now let's go ahead and start to build our application. So this is something that is familiar and common. I would not talk about the parallel processing or scaling the computations. You can do that seamlessly. The next thing again is the image data store. So whether you are doing conventional image processing, you are doing machine learning, or you are doing deep learning kind of workflows, you can use image data store, and irrespective of how big the data you have. So right now we have 3 different classes, 16 images from each class, so 48 of the images you can see. And 3 classes that we are looking at is babesiosis and other 2 classes for the infection. Now, we talked about many of these different functions that are associated to the image data store. Some of these functions that, like one of the functions that I have introduced was read image last time. Now here is another function that does count each label. Now this also becomes very important when we are doing the image processing and when we are doing deep learning or machine learning. Why? Because if we have one class, if we have the data for one class to be sufficiently large in compared to the other type of data, other class of data, then the model that we are going to train would be inclined or biased towards the class for which I have more data. So the first thing that I wanted to understand from my data is what is the individual count for the different classes. And here it's 16, but most generally when you're working on large problem statements or more commercial kind of a problem statement or research problem statements, the data set would be immensely large. Now, the first thing we understood what are the different number of labels or number of data samples that we have for individual classes. The next thing is I may want to start doing the visualization of what I'm dealing with. So here I'm just choosing 3 of the images of individual infections and displaying it for the analysis. And you can see, like looking at the image itself, we can see that probably like the babesiosis or plasmodium or trypanosomiasis could be 3 different kind of problem statements that I'm working on. Right. You can do a lot of different things from within the this display tool itself. Now, the next thing that we want to do when we are working on machine learning or deep learning kind of workflows is I want to split my data into training, testing, and cross-validation. So here I'm splitting my data into training and testing set, and split each label is one of the commands that will help me do that. And how it will help is I can directly pass the data store. This is another function which is associated to data store, wherein I can just pass the percentage of data that I want to use as training data, and then the remaining would be used as testing. This can also be used seamlessly with if you're trying to split the data into training, testing, and cross-validation. You can use this function right away as well. Now I'm using this function to split my data into training, testing, cross-validation, and then I'm also counting the pixels that are available inside the counting the number of the data samples that I have available for all these 3 different classes. So all these things becomes very important when we are establishing the workflow for doing machine learning or deep learning. Now, this is what just we are getting started when we are trying to visualize and analyze the data. Now, the next thing that is important is pre-processing. And in pre-processing, it becomes important for us to extract the features from the data. Now, when we are trying to extract the features, there could be a lot of different features that we may want to extract. It could be as simple as the statistical features like mean, median, kurtosis, and many others, or it could be more advanced features like case or Harris and many other, depending upon the application that you're working on. Here, what I'm trying to do is I'm trying to use bag of features to extract a lot of different features from my data. And what bag of features does is it actually creates the dictionary of the visual vocabulary. So it will create the dictionary of what are the different elements that you may see in your image. And once you create that dictionary, you can use that dictionary to further do the classification. So if you see here, what bag of words does is, first thing is it extracts the features from the images that we are providing. And then you can specify what percentage of the strongest features you may want to use. And then it is using k-means clustering to cluster those visual words into different classes. So here it is creating the visual dictionary for 500 words for each of the individual classes that we may be working on. Right. The bottom line here is we need to extract a lot of features, and I'm using bag of words as a feature extractor here. And these are the visual occurrences, visual word occurrences, or these are the different words that are extracted from the individual data set. And these are like the bar chart that you see is the frequency of the occurrence of these words within this data. Now, once we have this information extracted, we have the vocab built for individual classes. Now I can go ahead and try to train my model for these kind of for this particular kind of application. Now, I did mention this in the past also, when it comes to training the classifier for machine learning model, there could be a lot of different machine learning models available. It could be as simple as linear classifier or a logistic classifier, or it could be as complex as ensemble classifiers or support vector machine or boosting algorithms and so on. So inside MATLAB, there are a lot of
So participants, has he lost connection? I think so.
I think we've lost Rishu. So yeah,
Let's wait for he will join soon, but I hope so.
Sure. Yeah. In the meantime, in case there are any questions that anyone wants to kind of put in, please feel free to kind of put those
Yeah,
in.
Ashwin has raised hand. I'm just unmuting him. Ashwin, yeah, he was asking some question. I asked him, requested him
Dr.
to.
Gupta,
Yes, Ashwin.
which thresholding algorithm, in your opinion, is better, OTSU versus information theoretic, this cross entropy thresholding, in case you have used both?
Yeah, thanks, Ashwin, for the question. I don't like I wouldn't say yeah. So since Rishu isn't here, so I would say like the algorithm which can kind of does the job, like just pick those and maybe uh, look at the simplicity of like pick the simpler algorithm of the two. If you are getting good results there, then move on to the others. So based on that, I would say like say if Otsus does the job, then then that is good enough. I would say then no need to kind of go for
Okay.
so
And
that would
yeah, another second question now, bag of words and other machine learning algorithms have got limitation of feature sets when their feature sets is very large. Then we go for deep learning. So like even in some cases it might fail. So you need to draw a line when you need to shift to deep learning domain. Any
Sure.
inputs on that?
Here again, like yeah, so I would say that if you're looking at uh, deep learning versus machine learning, yeah, I think higher issue. Yeah, so Saroja, if you could maybe make him host again.
Yeah, just give me a minute.
Sure. Yeah. So yeah, on that front, yeah, where do you exactly draw the line between machine learning and deep learning? So whether bag of words might fail in some places, then what do we do in that case? I would say again, like so that depends on how large a data set or how much are the features which are there. Yeah, I think Rishu's back. And also one thing which I would like to add is like, in many cases, especially in when working with medical images, you might also need to look at explaining why a particular uh, machine learning algorithm or a deep learning algorithm might be behaving as it is. So while great strides have been made on the deep learning explainability bit, again, you may want to kind of focus on using a machine learning algorithm which gives you a greater explainability on why an algorithm works or why it fails or in which cases it fails, versus in deep learning where you may have limited control over that, right? So yeah, Rishu, if you would like to add to that, like why select like what's the line where you would select machine learning versus deep learning, and in case bag of words fails when
Yes.
there are a lot of features, then what do you do?
Yes, awesome, and thanks, Praful, for taking that up. And sorry, the power cut happened, and I was off for a couple of minutes. So that's a great question to ask. And one of the ways to choose between machine learning and deep learning could be see how the machine learning works. Is you need to extract the features, and more relevant the features are, the more robust, accurate, efficient your model would be. So it's a trade-off between the data. If you have huge amount of data, no domain experience, you go with deep learning. Deep learning will give you a lot of features automatically, which can automatically train and give you the best-in-class accuracy. However, there could be many use cases wherein the data sample that you are collecting is not large enough. However, you have experts on your side, radiologists, doctors, pathologists, that can give you domain insight. And given that domain insight, you may extract very relevant features, which can then help you build a model which can be very robust. So like I hope I answered that, but I'll try to reiterate. One of the lines that you can think of is if you have huge amount of data, no domain experience, or if you have huge amount of data with domain experience. If you have lesser amount of data, great domain experience, lesser amount of data, less domain experience. So this could be 4 different buckets in which you may want to classify picking machine learning or deep learning from the data perspective as well as the domain expertise perspective. Right. And when it comes to machine learning itself, there could be a lot of different features. So if you are going with a domain expert, he will tell you what features to extract, at least visually. And then being a data scientist or being an engineer, you will try to find a way to extract those features. The other way could be you extract a lot of different features, like you extract mean, median, mode, quantiles or kurtosis on the statistical front. Then you go ahead, extract bag of features. You go ahead, extract more dynamic features like surf, sift, case, or minimum eigenvalues, Harris. So you extract all of those different features, and then you try to build a model with those features and see what works best. Absolutely. There is a point in the chat window. The same analogy that I'm mentioning can also be extended to other applications other than medical imaging. Absolutely, it can be. Right. Perfect. So is my screen shared already?
Issue. We can see it.
Okay.
It's
perfect. Thanks, Praful. So let me get started with where we were. Right. So let me go back a little. So what we were trying to do was we were trying to extract the bag of features as one of the mode, and intent here is not to show you that bag of words best is the feature that works best for all of the different use cases. The intent is to show you that there could be a lot of different ways to extract the features. And once the features are extracted, you can use those features to train the model. Here I'm using a bag of features just as a representation to get large amount of features. Now, once I have extracted those features, the next thing is I may want to go ahead and train a classifier. Now, to train a classifier, there are a lot of different classifiers available, and there are a lot of different libraries which are available, wherein you will feed the features, you will feed the training data, and they will train and give you certain kind of accuracy. Here, the function that you see here, train image category class, this basically underneath trains a support vector machine learning model and tries to give you certain accuracy on the data that you're working on. Right. And then there are straightforward functions like evaluate and so on, which will try to give you the accuracy on the test data. So you already have a training data from which you are extracting the features. You have test data. From the test data, you will extract the features and push it to the evaluate. And within the evaluate, you will push in the classifier that you have trained. Right. And you will get certain accuracy. Here you are getting 60% accuracy or 0.6 as an accuracy. But the intent here is to show you can quickly go ahead and train your model. There are a lot of different workflows available. Now, I did mention there could be a lot of different classifiers or models that are available that you may want to try out your algorithm with, unless or until you get the most robust ones. Now, to address that, what we can do is we already have extracted a lot of features, and let's say I'm trying to classify based on the features that based on the analysis that I have done, I'm getting certain accuracy out of it on my data, but I wanted to go ahead and be more robust on the data as well as more robust on the model and see what other models may work best for my application. Now to do that, there is a way in which you go ahead and train individual different machine learning models, like just now we did with the support vector machine. However, there is one more thing that you can do inside MATLAB, and that one thing is you can invoke something called as a classification learner app. So let me go ahead and talk a little bit about the classification learner app. And what I'm doing here is I'm just encoding my features that I have extracted into a double, which can then be fed inside the classification learner app. So let me just go ahead and do that, show you the 500 features that we have extracted as a bag of features. So these are the different features that we have extracted around my data. I will organize these features more appropriately so that it can be fed inside this classification learner app with all the classes that you see on the right. Right, all the classes that you see on the right. And like invoking classification learner app, again, it was very brief. Again, to invoke classification learner app, you can go inside app section and you can choose classification learner app. Within classification learner app, you can start a new session. You can bring in the features that you have extracted. So here I'm going to choose the infection image data feature that I have extracted. I know there are 500 different features that I have, and there are 33 data samples that I have available for myself for training. Within the app itself, you can also choose whether you want to go for cross-validation, you want to go for holdout validation, or you want to go for no validation. Definitely, if you're going for cross-validation, you'll need to provide data for that as well. But there is a provision to do that. Now, this particularly app automatically recognizes that from the feature vector or feature table that you provide, it automatically recognizes what are the different columns from which the features needs to be picked and what are the different categories that are available. So it automatically recognizes there are 3 different categories. Within this app, you can do the lot of different kind of analysis right away. Like I can look at the different features and do the comparison with the help of this scatter plot. Or else, once I am done with this, in many of the cases, you may have like thousands and thousands of features extracted. When there is no domain expert, we may want to extract as many features as we want. Or if there is a domain expert, still we may want to go ahead with a lot of features to bring in variability and robustness in my algorithm. Now, out of the box, you can click on feature selection, and if you want to handpick the features that you wanted to try out with, you can do that. Also, you can introduce something called as a principal component analysis. Now, principal component analysis is one of the methods of dimensionality reduction. And by dimensionality reduction, what I means is, let's say you have 1,000 features that you have identified. So your feature table may look very, very large, and training that feature table can take a lot of time. So what principal component analysis will do is, principal component analysis will allow you to extract the variance or the information from that feature table and concise it into 2, 3, 4 feature vectors, which then you can take for training. And generally what has been seen with PCA, if you choose top 20% features, you get 98% of the variability in your feature vector or feature table. So it's up to you whether you want to go with PCA, you want to go with feature selection, or you want to go train with all the features that you have identified. Now that's one thing. The second thing is, like I mentioned, there could be a lot of different machine learning models that you may want to try out with. Right now, we tried with just one variant of support vector machine. However, when you are working on machine learning, there could be a lot of different machine learning models. Like it could be discriminant analysis, decision trees, logistic regression, Bayes classifiers, support vector machines, ensemble classifiers, nearest neighbor, and many other. From within this particular app or API, like I said, you can programmatically train individual models, or to get a immediate, quick bird's eye view of what model may work for your application. You can quickly choose these different models. You can choose all of the models, subset of the models from this model type, and train these models. And this also you can use to scale the computations on all the different cores you have. On the left, you can see I am training 4 different models simultaneously. And depending on number of cores I have, it could be 20, 25, 64, whatever cores you have. You will get the accuracy, and this accuracy will be based on the default parameters, which is available to train a support vector machine or a median Gaussian support vector machine. Now, default parameter could be good for certain applications. They may not be good for all the applications, but like for all the functions in MATLAB, these models also come with the default parameters. But what you can do on top of it is, you can always go back. Okay, before that, once you have this certain kind of understanding on the different models and the accuracy that you are getting with those models, you can start to do a lot of different visualization. You can visualize the confusion metrics directly on what's the true or the predicted classes, numerical values. You can also do rate-wise analysis as the true positive rate, false positive rate. You can also compute the ROC curve, and a lot of different analysis can be done right out of the tool itself. The other thing that you can do, and you can continue to build on, could be you can continue to add on through different models in order to see what model gives you best accuracy. So here I'm choosing another model, I'm retraining, and continue to see what works best for me. Now, any of the model which, let's say I'm having a support vector machine median Gaussian variant of it, and I want to further go ahead and explore and do the analysis to see if I can further optimize my model. So within this app itself, you can click on advanced and go to hyperparameter tuning, or identifying the best parameter within the support vector machine. So you can choose between the different strategies to do the optimization. Like you can choose between the range, you can choose between the stopping criteria, you can choose between different strategies like Bayesian optimization, grid search, random search, and all those things. And once that is done, you can again retrain the model. And the expectation is when you are retraining the model with the more optimal feature based on your understanding, the accuracy should be higher. And that's what the expectation, and that's what generally happens as well. So you start with some baseline accuracy, and then you continue to build on top of it. You do all the different kind of analysis, visualizations. You can export all these different charts. You can also put the misclassification cost, which becomes important if you have significant imbalance between the different classes that you are working on. So all these things can be very well done within this particular one classification learner app, all the analysis, visualization, and you can export these figures that you are doing the analysis on. When you are trying to publish the research paper, these kind of charts becomes very important, and getting access to these charts out of the box becomes significantly time saving. Now, similar to other apps that we have talked about, from within this classification learner, also you can export the functions, and also you can export the trained model. Now, this trained model can be very well taken for code generation or deployment as well. Right. Now, once you do with all of those things, you can again take your trained model and go back and do the analysis, and all the like advanced modification or advanced hyperparameter tuning, everything that you are doing, all the information gets saved inside the workspace variable. Once you are done with, like, good with all of these things, you can go ahead and you can do the testing. Now, many a times you could be working on just identifying good or bad. So you can also train your 2-class classifier and say whether the work application that you're working on is the images that you're working on are good or bad. So all these different options are possible, and it will, like, working with these apps will help you be more focused on what is where you need to focus on, rather than trying out all of the different things at first and then going ahead and choosing the best one. Here you know on the conventional side, these are the things and these are the certain accuracies that I can get, and now I have to build on top of this. Right. Great. Just a minute. Perfect. Now I'm starting to go into a little bit of deep learning. Just give me a second. Right. Now I'm starting to go a little bit into deep learning, and we already have talked about this a little bit. I'll just reiterate very briefly and I will move on to deep learning piece. Now, what is the major difference between machine learning and deep learning? I did speak about it, but I'll again talk about it briefly. When we are talking about traditional machine learning approach, you have a data and you extract the features from the data, and then those features is what your model gets trained on. You do not directly feed the data into a model. And this is the biggest difference between machine learning and deep learning. Machine learning, you extract the features and the model gets trained on those features and gives you the classifications. However, in the case of deep learning, you directly feed in the data to a convolutional neural network or CNN architectures, and CNN architectures automatically learns to extract features what is relevant for end application that you are trying to do. And once those features are learned, if you pass and the model is learned, you pass in the input image or the test image, and the expectation is if the model is trained robustly, you should be able to get the right classification or detection or semantic segmentation. Now, also deep learning approach is called as end-to-end learning because these two pieces from the machine learning is clubbed together. Feature extraction or feature learning is something that happens implicitly in deep learning as compared to explicitly identifying the features in machine learning, right? With machine learning, we have seen that we have started with accuracy of somewhere around 60%, and quickly we have scaled to an accuracy of around 91%. Now we will see in the deep learning how we can continue to further improve the accuracy of the application that we may be working on. Or what we have observed is if we have sufficiently large data set and if we define the network architecture appropriately and we define the hyperparameter and we choose the hyperparameters appropriately, deep learning can give us much better accuracy in many of the state-of-the-art problem statements, right? Now, one of the things that I want to highlight is machine learning is being, deep learning is being used in all of the different applications. And why so? The reason for that is because of the robustness of deep learning architecture. Now, this is a very high level deep learning architecture that you may look at. This is more of an ANN kind of architecture, wherein you have an input layer, there are a lot of hidden layers, and there is an output layer. And like all of these different circles or neurons are connected with the help of connections, and each of these individual connections represents a parameter or a hyperparameter. Okay, it's terminologically it's called parameters. So each of these connection between an individual neuron to the other layer is represented by a weight and a bias. And this flexibility in the neural network architecture to be able to learn these many different kind of parameters and extract these different kind of features gives this flexibility to use deep learning in multiple different applications. One other point is, if you can represent your data in the numerical form, you can use deep learning to solve the application. For example, if you're working on images are nothing but a pixel, and pixel is nothing but a numerical intensity value. You join these pixels or the intensity values in the form of a matrix and you see an image. In the case of deep learning, there are two ways to apply deep learning to images. One is you unroll the entire image into a single vector and then use the conventional ANN kind of an approach. But that's not very smart. For images particularly, you can use convolutional neural networks, which are the basic building blocks for image processing or computer vision applications as well. And what deep learning is best is it extracts those many features depending upon the number of the convolutional filters that you are defining. Okay, now let's go ahead and look at deep learning based classification of parasitic infection. When we talk about the deep learning workflow, three things are important. First is data preparation, which is also important in the case of machine learning. Second is AI modeling. In the case of machine learning, before AI modeling and in between data preparation, there was pre-processing, wherein you are extracting the features. However, in the case of deep learning, it's data preparation, followed by AI modeling, followed by deployment. Now, this process is not a one-time process. Deep learning could be an end-to-end approach, but this is not a one-time process. It is an iterative process. You go back and forth between your data, you go back and forth between your model, hyperparameters, and so on and so forth. For example, you have a set of data, you use that data to train a model that you have defined, and you get an accuracy of, let's say, 75%. Somebody comes to you, says that increase the data. You kept on increasing the data from 75% accuracy, you reached to the 85% accuracy. But now even improving the data or increasing the data set is not helping you. What next? Then you will go, you have saturated your limit to bring more and more data. Now you may want to explore some other parts. Now you may want to go ahead and modify the network architecture, probably play around with the layers, probably play around with the different network architectures, probably see transfer learning as an approach, many other things. So once you're saturated with data, you may want to go ahead with the different kind of models, or you may want to choose different hyperparameters within the models in order to converge to the accuracy and robustness you want. So deep learning may still be called as end-to-end learning approach. However, there are a lot of different variables. There are a lot of different components that needs astute working in order to get to the robustness and accuracy that you want. And we will look through all these different challenges and how you can address them while doing deep learning. One thing that I want you to take from this slide is there are 3 different pillars to deep learning. One is the data preparation, another is modeling, and the third one is taking it and exposing your application to the end user. And this is an iterative process. It is not one-time thing. Okay. Now let's go ahead on the data processing side. On the data processing side, 2 things are important. One is, how do I access my data? And second is, how do I label my data faster? Let's go ahead and talk about how do I access large data sets, which I have talked about previously also. Inside MATLAB, depending upon the kind of data you are working on, there are different kind of data stores available. If you're working on images coming from, let's say, CT, MRI, or ultrasound, you may be working on image data store. If you are working on images that are histopathological or macroscopic images, then you may want to invoke something called as big image data store. Big image data stores capabilities are specifically to handle large images. And then you may be working on certain kind of data for which the data store is not available altogether. So there you can build your own custom data stores. If you're working on numeric data, there are tall arrays. And let's talk more about the big image capabilities. Now, there is an object, or there is a functionality or a function inside MATLAB which is termed as big image. And the main intent to have this big image is because many a times what happens is, if there are multiple files, large data can be of 2 types. It could be thousands and thousands and millions of images which comprises of your data set. That's still a big data, but the individual files in that data is a small. And there are a lot of ways in which you can process that data. You can use image data store, you can chunk your data into different components and then process it. Like, there are mini batch sizes, there are epochs, and a lot of different hyperparameterization that you can do there. The big challenge comes when you are working on very large images, wherein you don't have multiple files, but you have one large image and probably 3 or 4 such large images, and you want to train your model on that. So that's where big image capabilities becomes handy and helpful. The purpose of big images are to handle the images which do not fit in RAM. And to read the big images inside MATLAB, like similar to the normal images, it's IMRead. For big images, it's BIG image, big image, to read those images. Right. And if I'm not wrong, this big image is also has something called as a blocked image on top of it, which facilitates the similar thing. Now let's look at big image a little bit more, how it can help you in visualization as well as how it can help you in processing of the large images. Now, the first thing is you can use all the capabilities inside MATLAB with the and scale it to as many cores or layers that you have. Now, while you are working on these large images, many a times they provide you information on many different levels. There is a coarse level and there is a fine level. So with this particular function, you can read in one shot all of the different resolution levels that are available in your big image. Once that is done, you can start to go ahead, create your big image object and do the visualization. And while you are doing the visualization, it doesn't load the entire image. It loads the image on the fly while you are trying to zoom in or zoom out into the data that you are working on. Right. Now, the second important thing is you can dynamically cluster your images into different segments or grids, and you can start to work on individual grid. And you can do this at different resolution levels. You can build your algorithms at the coarsest level. So I can build my algorithm on the coarse level. So I can build my algorithm while working on the coarsest level, and same algorithm I can directly scale onto the finest level. So I'm getting the low resolution image. I'm trying to build an algorithm with that low resolution image, and then using an apply filter to apply that function that I have created here, I am binarized onto that my finest resolution image. So you are not working on the large image right away. However, you are working on the smaller image or a subset of an image, getting an algorithm right, and then using this simple apply function to apply that particular algorithm onto the finest resolution scale. And this apply function is very well supported again with the computation scale term, that like you can use it with the different cores that you have on your machine. Here I'm doing it on a single core, but if you also want to take this and apply this onto the multi-core thing, it's also very seamless and easy to do that. So that was, and if I want to do take it to the multi-core on my machine, I will just invoke this name value pair inside MATLAB to true, and it computation automatically scales to your whatever compute resources available, and you will get the similar outcomes. So this helps you to process the image chunk by chunk. This helps you to process the image at finest coarsest level and do the visualization of these large image on the fly. Right. Like I said, the capabilities of big images are mostly to process the large images which do not fit in RAM. Big image wraps around the big image creates a wrapper around the large images that you are working on, and these image pixels are not loaded all at once. So if you have observed while I was trying to zoom in and zoom out, the image pixels also were loaded as and when needed for visualization as well. We have seen this, it supports multiple resolution level. If the data that you are working on has the multiple resolution levels of images, you would be able to directly read it and do the analysis, algorithm development, as well as scale your computations, as well as algorithms to from the courses to the finest levels. We routinely test this with a very large image, which is 90K by 90K size, which has 24 GB memory on RAM. So, but that, like, I have seen much larger images than this while working with some of the users on the satellite images as well as medical images. So we do this routine check with this size of the image, but the capabilities are much far beyond this and can be scaled to whatever compute resource, whatever kind of image or data you have. Now, similar to the big image, similar to the image data store, the capabilities of big image data store also is accompanied by a lot of different functions that we have seen, like read image and all. So you can use a big image data store in conjunction with image data stores right away. The next thing that I wanted to come on is the modeling piece. Now, modeling piece is where you will design your neural network architecture, choose what kind of hardware you want to do the training on, and train multiple models in order to get to the accuracy that you want. Let's go ahead. Now, for all the things that we have been seeing today, you can establish a command line workflow, or you can do the scripting in MATLAB. Also, you can go ahead and do, for many of these framework, there is abstraction available in the form of apps, which you can use to quickly build your applications and do the analysis. So if I talk about the API, if I talk about the command line interface, reading any of these pre-trained models inside MATLAB is just single line of a code. You can call in these networks inside MATLAB. There are a lot of pre-trained models which are available. You can do all different kind of analysis, visualizations as to what are the different weights, biases, and everything that is available inside that network. And if you want to use that to classify the image that you may be working on, you can just quickly read that image and use a simple function called classify to classify the image as per the network that you have downloaded. And AlexNet, we all know that is not trained to classify the medical images. So the class that you saw here was a honeycomb, which is little bit similar to what this image looks like, but it's entirely a different category of application that we are working on. Now, I can use image data store to read the image. There is one other function that I'm introducing here, which is image data augmenter. Image data augmenter gives you flexibility to augment the data set on the fly while training. Different kind of augmentations that are available is scaling, sharing, translation, rotation, reflection. But if there is a need to build other kind of augmentation pipelines as well, that can be done as well. But this image data augmenter provides these kind of functionality out of the box. And you can go ahead and do the training. But before that, let's look a little bit on the transfer learning as well. And in transfer learning, what may happen is you may want to just modify some of the final layers. So we have seen AlexNet has 25 layers. And what we are going to do is we are going to just change layer 23 and 25th. Layer 23, AlexNet has 1,000 classes. However, in our use case, it's just 3 classes. And the final is the classification layer, because it needs to now accommodate to the feature fully connected layer of 3 classes. To train a neural network, I simply define a function named as training options to define all the hyperparameters, like what is the optimizer I want to use, what is the solver I want to use, what is the learning rate, epochs, batch size, and all. And you can also plot the training progress plot. From within training option, you can also choose what compute resources you want to use, whether you want to scale to GPU, CPU, multi-GPU machines, or to cloud or cluster. Right. So once that is done, you can simply invoke. And here, what I'm doing is I'm using augmented image data store and passing in my augmented images, right? And once that is done, this is something, a training progress plot that you can see. You can visualize how your training is progressing, how the losses are decreasing. If it makes sense to you, let it happen. If it doesn't make sense to you, just cancel it, go back, redo the hyperparameterization, and see what works best for your application, right? You can plot the confusion matrix, you can do the analysis on the test images that you have. And once we have done that using transfer learning, now you can see when I'm trying to do the classification, the AlexNet after transfer learning is doing the right classification. Now this was from the command line workflow. I can do all of these things inside something called as a deep network designer as well. Now, deep network designer is a graphical or a visual API which helps you establish this entire framework. So here are a lot of pre-trained models which are made available. You can choose any of these pre-trained models for transfer learning if that's the use case, or you can architect your own neural network architecture as well from blank canvas. Here I'm choosing AlexNet. AlexNet has 25 layers, 24 connections. It's a classification kind of network. However, my interest is to do the transfer learning. And for transfer learning, what I would require to do is modify some of the final layers. Here I am bringing a fully connected layer, removing the other layers like the classification layer, right? And reparameterizing these layers on the right panel. So here I have reparameterized for the fully connected layer, and now I'm reparameterizing for the classification layer. Once all of that is done, I can do the analysis of my neural network architecture that I have created. And once I am done with my creating the network architecture for my application, I can quickly click on data, because this app not only helps me designing the neural network architecture, it also allows me to import the data and do augmentations from within the app itself. So I can import the training data, I can import the validation data, or I can split my training data, validation data from the training data, and I can have a lot of augmentations done on my training data out of the box. Once all this is done, the augmentations, whatever required, I can quickly go ahead and I can do the training. So now for training, you can see all of these options available. What is the execution environment? If you click on the drop-down menu, you will see all of the different CPU, GPU, multi-GPU, parallel kind of options available. Depending upon what compute resource you have, you can scale that. Now, once you are done with the parameterization setting or hyperparameter setting, you can quickly click on train, and this will automatically start to train your neural network architecture. Right. So whatever we are doing from the command line can also be done from the graphical API based workflow. One other very important piece that I wanted to highlight here is while you are training a deep learning model, there are a lot of variabilities to it. And you may want to do multiple iterations. How to do those iterations, how to keep track of those iterations. There is something called as an experiment manager. Within experiment manager, you can define your experiments. It's very easy to set up the experiment. Once you set up the experiment, you choose what are the different hyperparameters that you may want to tune on. And once you choose those hyperparameters, you can define, like, this is more of a textual information that you are providing, and this is more of the lower level information as to what are the different kind of solvers I wanted to choose. Like I'm choosing add-ons, RMS prop, SGDM. Then what is the learning rate? What are the different network choices? You can have as many of these parameters or hyperparameters here. You can define your own metrics and all. Once you do all of this setup, you can quickly click on run. And as soon as you click on run, it's what I have chosen here is an exhaustive source sweep methodology for training. What happens here, it automatically pulls down all the permutation combinations of the different hyperparameters that I wanted to tune on. And once that is done, it starts to iteratively tune my or train my network architecture, and also gives me a metric level accuracy, whichever metric I'm defining. I am defining here training accuracy, training loss. You can have your custom metric that you may want to define. Right. And you can choose the best network that has the maximum accuracy. You can put certain annotations around it. You can export that network as well as the training information. Right. The other thing that you can do is you can choose between the different optimization strategies. That was exhaustive sweep. You can also choose to have Bayesian optimization. And in Bayesian optimization, you will need to reparameterize these depending upon what Bayesian optimization expects. And you will also need to define the stopping criteria. Once all that is done, you can again click on run. And this time you won't see all the permutation combinations here. Sorry, you won't see all the permutation combinations here. Rather, you would see this learning on the fly with the help of Bayesian optimization. One of the flags that you may see is I'm doing the iterative training of one neural network architecture, but that's not the case. You can also use multiple cores of your machine and actually do the training using all of the different cores that you have access to. And you can keep track of all the neural network architecture or the trials that you have done in the past in the form of the training information. You can understand how the network is evolving with what data, with what architecture, with what hyperparameters. This becomes very important when you are working on larger scale applications. Awesome. Now, one piece that I wanted to talk more about is the deployment piece, which is there is something called as an app designer, which allows you to interactively build an app. And once the app is built, it also gives you option to like you can write all the functionalities of the app and whatever. And then you can also compile this into a form of an executable that can then be shared either over the cloud, or it could be shared in the form of a exe, where you are creating a standalone desktop app. So here you can see I'm selecting an image. Once the images are selected, I am quickly classifying the pictures based on the network that I have behind this select image function or the button. Once that is done, I can do the analysis of individual images and I can export my results as well. So within one tool, you can share this tool with a pathologist, radiologist, or you can, depending upon what's the use case, you can share it across with different users. This particular one app could help you to import the images, do the classification, and also export the results right away. Right. Now let's look at the last use case that we wanted to touch upon, and which was semantic segmentation for the cardiac left ventricle cardiac image. So when we are talking about the semantic segmentation, there could be a lot of different kind of neural network architectures that you may want to choose from. It could be SegNet, it could be fully connected networks, it could be UNet, it could be DeepLab v3, or you may want to create your own network architecture. While you are working on these semantic segmentation networks, you may also want to choose many different pre-trained models to get started with on top of it. because you build a semantic segmentation network with the help of certain classification network by picking a specific layer from which you wanted to reconstruct the semantic part. Let's go ahead and look at the workflow there as well. So first thing is we will label the data for the left ventricle from the axial cardiac cine MRI images. The second is we will apply the semantic segmentation and train my network architecture. Second is once the training is done, I will use that trained network to do the semantic segmentation on my incoming images. And doing on multiple images will help me also to get the volume of the left ventricle as well. So this is when done on one images. This once you do with multiple images, you slice it and you create it, convert it into a form of a volume. Right. Now the workflow here is again the same. You do preparation, you do modeling, you do deployment. Finally, on the preparation side, first is you may want to visualize the data. And for visualization of these 3D voxels or the volumetric data in MATLAB, there is something called as a Dicom Viewer. Before Dicom Viewer, there is something called as, just let me wait, sorry. Right. I'm sorry here. So before doing the 3D analysis on the volumetric data that I have, I would want to just do the analysis. So for that, something called as Dicom browser is there, wherein you can bring in all your Dicom images that you wanted to analyze, and you can do the analysis of those Dicom images in the form of just visualization. So you can see all of these different images. You can select these images. You can also visualize all the metadata that could be there pertaining to those images. Right. Now, the second thing that I want to highlight here is volume viewer. The entire data that you have in the form of 3D slices, you can bring this inside this volume viewer app as well. You can do the analysis in the form of a volume, or you can slice different slices. You can do the analysis in the XY plane, YZ plane, ZX plane, and understand what your data looks like. Right. You can also do some bit of a pre-processing here. Right. You can also do the volume rendering, different kind of methodologies to do the rendering as well. So all these kind of visualizations is possible within the volume viewer app. You can also bring in your labeled data within the volume viewer app and overlay it onto the volume and do the analysis. The next thing that I wanted to talk about is the labeling piece. Now, I haven't introduced the labelers yet in MATLAB, but there are a lot of different labelers available, like image labeler, video labeler, and so on, depending on the kind of data you are working on. So when I'm working on medical images, those are generally discrete images. So I'll invoke the image labeler app, and image labeler app comes with a capability to help me do the labeling of the image. There are a lot of capable, and you can directly import the Dicom images within the labeler apps. Once imported, you can do the visualization of those images as to what those images look like. You can start to identify or define the different kind of class labels. And also you can choose between different kind of annotations that you may want to have. You may want to have a rectangular box, semantic labels, or cuboid labels if that's relevant, but not in this case. So you can choose between different kind of labels that you may want to have in the case of semantic segmentation or object detection or classification. So once you choose that, you can use the tool itself to quickly start to do the annotation. So here I'm doing the background as well as left ventricle. And there are a lot of capabilities available within the tool itself to help you do the annotation. But that's not the intent, because what I really want is to automate my labeling process. To that, what I have done here is I have trained a semantic segmentation network, which can give me the annotations for left ventricle and background. Now, if I have an algorithm that can give me some fair idea about the proposed labels, I can use that algorithm within this app to give me initial level of labels, and then I can continue to modify those labels. So once selected, I can click on automate and I can click on run, and this is what the automation may look like. So I'm having a background, I'm having a left ventricle images that I see here. Right. I can do the modification if the proposed labels are not correct. I can come back, because in the case of medical image, I need to be very precise for the labels. So I can come back. I can do the modification to the proposed labels. I can retrain my algorithm, bootstrap the entire process. In the process, I could be getting very accurate model that can give me very accurate labels. The third important piece, you could be working on the image labeler, or you could be working on big image labeler. Big images and big images capabilities is also incorporated within the labeler apps itself. Now, the third thing, once you have the data streamlined, it would be model development. And for model development, for semantic segmentation, what you can do is, first thing, like I would skim through this piece little quickly, because this is the same thing that we have seen here. First thing is we need to bring in the data. So data store is something that we are using. And once the data store is done, I'm going ahead creating a pixel label data store to store my labels, because for semantic segmentation, I need to have a pixel label data store. There are other data stores like box label data store if I'm working on bounding boxes. Count each label becomes important because there could be significant bias on the background and the foreground. And then I can start to train my network. But before that, I want to do the augmentation and create the data for the augmented data store as well. Split my training, testing, cross-validation set. And here I'm building my network architecture. I'm taking VGG16 as my base network. And with the help of VGG16, I'm creating a SegNet network. However, if you want to create a UNet, DeepLab, V3, all those kind of networks, you can have a single command. You can provide the kind of the network that you want to choose for as a starting point, and you can create the network architecture right away. Once this network architecture is created, mostly from here, it's the same thing. Once the network architecture is created, you can directly go ahead, define the training options and all the parameterization you can do, and you can train the network architecture. Once the network architecture is trained, there is a simple function called semantic seg, which allows you to actually do the semantic segmentation of the image that you have or the data store that you have with the network that you have trained. The below I was doing it with the test data set. There is a function out of the box available which can give you a lot of different metrics against ground truth to see whether the network that you have trained is accurate or not. Metrics like Jaccard matrix, intersection over union, mean BF score, and so on. Great. Now, the final piece here that I wanted to talk about is we saw how you can generate an app out of the algorithm that you have built and share it across with different users. However, in many of the cases, I may be working on a standalone device. And in that case, I may not want to deploy my application using app. Rather, I may want to do a code generation which can be deployed onto certain embedded target. So that also is something which is supported out of the box, and you can deploy your applications onto embedded target by doing automatic code generation using MATLAB. So very quickly, to do that, if I want to do the deployment on NVIDIA GPUs, I'll choose GPU coder. Once I invoke GPU coder, I want to provide the entry point function. And here the entry point function for me is segmentation of the left ventricle. So I provide that entry point function, and that entry point function is doing nothing but loading the pre-trained network and running the predict command on the image with the semantic network that we have. So once I do code generation here, I can test my generated code right away from within the MATLAB itself. And once the code generation is successful, so here I have chosen the entry point function, then because when you are doing C++ code generation, important thing is to have the input and output arguments correctly defined. So I can use a test script to do that. It will identify what is my input image look like, right? And I can just go ahead and choose GPU to check if there are any runtime issues or performance issues, right? And once that is done, I can quickly go back to generating the code actually. And while I'm doing code generation, there could be a lot of different types of code I want to generate depending upon my use case. It could be as simple as DLL, static libraries, dynamic libraries, standalone executables, or you may want to just generate the code and bring it inside MATLAB for testing. So here I'm doing the code generation for Max. I can choose different kind of libraries that I may want to target on the NVIDIA GPUs. Right. And once this code generation is successful, what I will see is actually a MEX file getting created in my folder, and I can call this MEX file right away to do the test whether the generated code is right or not. So for entire algorithm development as well as code generation or deployment, you can establish the entire flow very much. There are a lot of apps available. There are command line APIs available, which will help you to save a lot of your time and quickly scale to either the research problem that you are trying to get onto or the product development that you are trying to do. Right. So these are some of the use cases wherein we have worked with a lot of different customers across the globe in the medical imaging domain while trying to use deep learning for semantic segmentation. Here, Genentech is using semantic segmentation and deep learning for segmentation of the tumor tissues from necrosis. And here, the University Hospital Heidelberg is trying to generate a high resolution CT image from the low resolution CT image that they are getting with the help of ultra low dose, which would help a lot, because when high resolution CT is taken, the patient needs to be exposed to huge amount of CT or the harmful rays, which can be radiations, which can be very painful and disastrous as well. Okay, so now just to okay, sorry about that. Yeah, so that's, I guess, all from my side. I thought I had one more slide to summarize this. Yes, sorry. So I would like to quickly summarize what we talked about today. We talked about how different apps can help us quickly summarize, quickly scale my applications, do the analysis and see what works best for my workflow. We also seen some of the large images capabilities, how we can work on with microscopic images or histopathological images. While I'm working on medical images, how I can also automate ground truth labeling to some extent, how I can create, validate, train my neural network architecture from the command line as well as from the apps, and also how I can deploy the applications that I'm building onto different targets. And while you're working on medical imaging, there could be use cases while you want to deploy these applications that you have built onto a cloud infrastructure wherein users can have access to it, or you may want to also deploy it onto a form of edge device. It could be Raspberry Pi, it could be Jetson, or it could be more advanced hardware, right? So I am little over time, but I hope this was useful. I'm done from my side.
Great. It was such a wonderful talk, and we really enjoyed, learned so many things about recent developments in MATLAB, especially for computer vision. There are a couple of questions people would like to ask. I can see some Femina Shiba. She's asking which DL model is best for blood smear images. So may I request you all, please raise your hands, and we would like to unmute you so that you can interact with the speakers. Questions, please.
Right. So in the meanwhile, I'll try to answer the question that Shiba has asked. So it's a very difficult question that you have asked, Shiba. I have to say that because when it comes to deep learning applications, for very specific applications that you may be working on, you may want to create your own neural network architecture. And the reason for that is because there are a lot of pre-trained models that are already available in this space. Like there is AlexNet, there is ResNet, Inception, lot of different kind of frameworks, lot of different kind of neural network architectures that are available. But those are trained on ImageNet dataset and proven on ImageNet dataset for accuracies like 99 or 100% accuracy. But ImageNet dataset is entirely different to the medical images. It's a dataset of optical images wherein you are trying to do the classification of cars, buses, trucks, and more of a real life examples that we are working on. So it's very hard to say which pre-trained model or which model would be best for medical images or blood smear images. But one insight I can give you is these models that we look in the public space like AlexNet, ResNet, Inception, or many advanced model architecture. These are already proven model architectures for certain applications, right? So what you can do is you take these model architectures and adapt these model architectures to your application. Exactly what we did with AlexNet and transfer learning in the use case that we talked about. Don't start from scratch to build the network architecture layer by layer. Start with something which is already available. Try to work with that, get data for your application, do the labeling, and then train with your data and perform transfer learning on these pre-trained models. These are highly proven network architectures. So there is no guarantee that there is no doubt that these are very robust network architectures. So my suggestion is start with these pre-trained models because they're already proven and adapt it to your application.
Thank you. I think Shiva, is that okay? I hope you have understood what he wishes to say. Any other person who would like to ask a question? Any other participant, please? Yeah, thank you, Shiva.
Okay. If there are no questions at this point in time, what I can do is probably let me quickly share my email ID. So my email ID is rishuji@mathworks.com. So feel free to, like, if you have questions, just let me know today or even at later point in time. I would be happy to reply to some of the questions that you have.
Okay. Thank you so very much, Dr. Rishu Gupta.
Okay. Wait,
Dr.
I was not
Pratyush
sharing my screen.
and Dr. Praful for your such a wonderful discussion and talk on this. Yes, I'm reading also if there is any message. No, okay, it's from Praful Raji. All right, so on behalf of Electronics and ICT Academies at IIT Roorkee, NIT Warangal, NIT Patna, MNIT Jaipur, and IIIT Jabalpur, I sincerely thank all three of you, for making this session so live. We could see so many things, so many options available. And you also touched upon some of the recent developments in the field. All these things, I'm sure that the participants are greatly benefited. We wish to thank you once again for helping EICT Academies in a big way. And I hope that you will continue to help us and support us in future. With this, I thank all the participants who are present here, and we look forward to meeting you in the next session at 6 p.m. Thank you.
Thank you very much, ma'am, for providing us the opportunity.
It was really wonderful. Such a nice presentation, and people must